then wipe it off, and then use the other side while the first side dries.
Okay, let's get started. How's everybody? So, couple announcements today. One is there is a quiz next week. Monday, I know, feels like there's a quiz every 2 weeks because there is a quiz every 2 weeks. So, Monday, November 12th, quiz 5. All right. Now, I was kind of hoping you guys would do better on quiz 4. I hyped up quiz 3, saying that it was going to be really hard, and you studied hard, and you did pretty well. Quiz 4, I did hype it up, so I guess you didn't do quite as well. Quiz 5 is supposed to be killer, though. Okay? And I'm not just saying that because I want you to do better. But quiz 5, the material is difficult. We're doing stuff like this. Okay? And you probably don't know how to do problems like this. Well, maybe you know the mass of this guy here, you know the mass of the stick. All right, if I put it in the middle here, you can guess what the forces are going to be on the two sides. Right? Half of the force of the weight of this and the stick will be half is here, half is there. Right? But suppose I change the problem and say that the mass is hanging over here, at like three-fifths of the weight or something. Three-fifths of it. Okay, then what exactly are going to be the forces? You see this one? It's less than this one here. We're going to learn how to solve that problem. And there'll be also these angular momentum problems, which are complicated than the problems we did last week with the kinetic energy of rotation, moment inertia. These are kind of tricky. Okay, so in order to prepare you for that, I have put more practice problems on the website. So in addition to the ones you already have, I also put in these equilibrium problems with solutions and these rotational dynamics problems with solutions. Some of these are really hard problems. And we tried to make the quiz fair. We tried to make it actually as easy as we could make it. But the problems are just kind of tough. So if you don't know this stuff, you're just going to get zeros or ones on the quiz. Okay? It's that tough. So you have to get top of it. Okay. All right. Now that I've scared you, I'm going to do everything possible to try to help you out. One thing I will do, my plan tonight, oh no, maybe not tonight, but maybe tomorrow night, I will record the solutions for quiz 4. So those of you who didn't do so well, I would like you to learn the problems from this. The other thing I want to mention as an announcement, for tomorrow, I will not take clicker attendance for those of you who want to go vote. Right? So find where you need to go vote. If you want to vote, find your polling place, go to vote.org and just type in your address. Okay. By the way, one of the things you vote on is the board of trustees for MSU, so if that's something you care about, you might want to go. Okay. All right. Okay. So, everybody had a chance to take a look at the material from last week. Either you came to class or you looked at the videos. I've seen quite a few views, so I think people are pretty on top of it. So let's just, we're going to talk about equilibrium, solving these types of static equilibrium problems, but let's just review the notion of torque, because torque's going to play a big role. If torque is kind of hazy in your mind, just, we need to review that. So let's think about, I'm having, yeah, sorry, this is in the way. Okay, so suppose I have little nut there with a wrench. Okay, and we have a force is acting here. And we have, this is the rotation axis. So whenever we talk about torque, we need to know about which axis we're rotating. So remember, this is a three-dimensional perspective, so the rotation axis is actually a line going through that point. And then there is this lever arm vector, which we just usually call R. Okay? So the first thing with torque, you got to know where is it acting. Oh, sorry, where is the rotation axis? And then where is the force acting? And then this lever arm vector, this R vector that goes from the rotation axis to where the force acts. Okay. So then the torque, tau, this is the torque. And in terms of the vector torque, it will be the cross product of R and F. Okay. Remember the cross product? All right, remember the right-hand rule? Remember that? Okay. All right, so let's first talk about the magnitude of the torque. The magnitude of the torque, remember the torque is the analog of force for rotations. It's how much twisting you're doing, how much twisting you are doing around some rotation axis. Okay, and so it will be the magnitude of R times the magnitude of F times the sine of the angle between them. So when you're drawing these angles for phi, you just simply draw the vector from the rotation axis to the point where the force acts, and then just extend this, and then you make the angle between those, for the force and this extension. Okay, times the sine of phi. Or just simply, in terms of magnitudes, it's just tau is equal to R times F times the sine of phi. All right, there is another way of calculating torque that is a little bit of a shortcut. So we can also write that tau is equal to R perpendicular times F, where R perpendicular is R times the sine of phi. It's clearly the same formula, but you might say, why is that a shortcut? Well, it's a shortcut in this sense. Suppose one of the forces that you want to calculate the torque for is pointing in, let's say, this direction. And let's say we have this is where the rotation axis is. And so we need the vector from the vector from the rotation axis to the place where the force acts. This is the lever arm vector. Okay, and then this R perpendicular thing is very simply, you draw a line that goes through the force. You just draw a line through it. Just make a line that goes through it. And then you say, how close does this line get to the rotation axis? So you try to go from the rotation axis down to the line. You go perpendicular like this. Okay? And that is what we call R perpendicular. Right? R perpendicular, which is R sine of phi. The reason it's the same as R sine of phi is because when we make this vector, when we make this angle here phi, it's the same as this angle here phi. And so this is the opposite side to the angle phi. R is the hypotenuse of the triangle. And so this is going to be R perpendicular. Okay? Any questions about this? So the reason why these R perpendiculars are sometimes useful is if the force is, if F is horizontal or vertical, using R perpendicular is usually faster. All right? Because if it's horizontal perpendicular, it's easy to draw this straight line through. And in fact, sometimes in the problem, they give you all the distances relative to vertical hash marks or horizontal hash marks. And so you can measure these R perpendiculars very quickly. Is everybody clear on this, what I'm saying? You can use either formula, R F sine of phi or R perpendicular times F. I'm saying when F is vertical or horizontal, R perpendicular tends to be a little bit faster. But you can calculate either way. It's fine.
All right, now, next thing I want to mention, so when we talk about torque, you can't just add up torques together because some are going one way, some are going the other way. So we talk about when we have a rotation axis here, okay, this is, which one is this? What do I call this? Okay, yeah, very good. So this is counterclockwise. And this is what your textbook calls positive. That's standard because that comes from the convention that when we measure angles, right, in the xy plane, we typically measure from the positive x-axis, we measure it counterclockwise from the positive x-axis. So that's the same convention. So if this is positive, that's the way we're measuring the torque, okay? Now if we go the other way, this is clockwise, and that's negative. So when you have a rotation axis, so suppose I have my pen here, and let's say the rotation axis is right at the center here. So I'm going to rotate the pen about the center. So if I have a force going like this, pushing this way, you just try to figure out, is it twisting my pen clockwise or counterclockwise? Which way is it twisting it? Everybody sees clockwise? If I do this way, everybody sees it going counterclockwise? Okay, notice if I push this way, which way is it going? Okay, most of you are not saying anything. So let's do it once more. So if I push this way, which way does it go? Okay, and this way is which way? All right, just want to make sure. Okay, now we're ready to talk about equilibrium. Okay? Now, the equilibrium we're talking about today is actually very often called static equilibrium. It's one in which the acceleration is zero, the net force is zero. We'll talk about the net torque being zero as well. But we're also going to have a situation where nothing's actually moving at all. Not only is acceleration zero, but it's actually not moving. And this is typically when you have a hanging structure like this, or a bridge or something. But the fact that the velocity is zero is actually not really that important, but in the situations that we're going to apply it in, it will actually be true that the velocities are also zero. So let's just say, we say that a system is in equilibrium if the net force F net is zero and the net torque tau net is about, let's just say is zero. Okay. Now, when you measure torque, you have to specify rotation axis. You have to say about which point you're trying to measure the torque around. Is it here, or is it going to be about this axis here? Okay. So you have to specify. You need to specify the rotation axis. Now, I'm not going to go into detail of proving the statement, but if you know that the net torque is zero about one rotation axis, let's say here, and you know the net force is zero, you can actually show that the net torque about another rotation axis, let's say over here, is also zero, and a rotation axis over here would also be zero. So if you can show that the net force is zero, and the net torque about some particular rotation axis is zero, it's true for all of them. Okay, I'm not going to go through the argument. Okay. So there is a little bit of freedom. You can choose any rotation axis you like. they are all equivalent. For showing equilibrium. All right. Very often, in order to keep things straight, sometimes I like to do the following. You can use positive or negative, but one of the things I've done in the past when I've taught this class is I like to write that the net torque is equal to 0 in this way. The sum of all counterclockwise torques equals the sum of all clockwise torques. That's one way to do it. Or you can just put plus signs for the counterclockwise and minus signs for the clockwise, and then they add up to 0. So this is equivalent. Same as saying that the net torque as the vector is equal to 0. Okay, I mentioned this word static equilibrium, so let me tell you what it means. So we talked about equilibrium, but the thing we will actually talk about, if I'm being precise, static equilibrium refers to what I just said, that the net force is equal to 0, and the net torque is equal to 0, and nothing is moving or rotating. Okay. All right, let's just do some simple math. Why not? Let's just do these as clicker problems. Yeah. Let's do these as clicker problems. So get your clickers. These are easy problems. You get easy points. Okay? All right. Let's see what you think here. All right, so we have this stick. Let's say it's a uniform stick, equal distances. These are the same distances. Okay? And our force is going perpendicular. Is this guy in equilibrium or is it not in equilibrium? Okay, everybody had a chance to click in? Give you another 10, 15 seconds. All right, make your choice. Okay, let's see what people said. Okay, it's 35-65. It's a little bit, there's more B's. Okay, so let's just apply the definitions of equilibrium. Equilibrium, net force is 0, net torque is 0. Okay, net force, I got 1 Newton up, 1 Newton down. So we have that the net force looks to be 0. Okay, we're halfway there. Now, how about the net torque? So I have this force here. Is it produced? This is my rotation axis. Let's take this as the rotation axis. Is the torque going to be clockwise or counterclockwise? From this one. Clockwise. Does everybody see that? you don't see that, you don't really understand the clockwise, counterclockwise thing. So if you can't see it right now, you have to get used to it, right? So the point is, you pin the thing here, and you press this way. Which way is the thing turning? That's what you have to visualize. Which way is it trying to move it? And it's clockwise. You see that? Okay. How about this force here? Is it making a clockwise or counterclockwise torque? Okay. So they're both clockwise. They're both clockwise. And so they add up. So it's not equal to 0. So it's not equilibrium. Okay. So very good. Now, we don't have to do these as quickly as well because these are simple. How about this case? Is this an equilibrium or not an equilibrium? Is it equilibrium? Remember, you have to check two different things. Right? Is the net force 0? No. Okay. So you need the net force 0 and you need that the net torque is 0. So the net torque in this case is 0. So net torque is equal to 0 because this one will produce, let's measure it around here, there'll be a clockwise torque from this guy. This will do clockwise. It's trying to spin it around this way. Whereas this one is trying to spin it around counterclockwise, and they will cancel out. Okay. However, the net force is not equal to 0. Okay. All right, now let's try to draw the simplest thing, non-trivial thing that gives you a net torque of 0. Something like this. 1, oops, sorry. 1 like this, and then 2. Okay? Does that make sense that that's 0? Okay, this is supposed to be in the center here. This is pointing up, pointing up. So the net force is equal to 0 because I have 1 Newton up, 1 Newton up, 2 Newtons down. They cancel out. And the net torque, is it equal to 0? Okay, let me show you a trick. So I said that you only need to check that the net force is 0 at any rotation axis. Okay? Okay. So what you can do is you can pick your rotation axis to be a place where one of the forces acts. So I'm going to take this to be the rotation axis. It's also the most logical one since it's in the center anyways. But what does the torque do to the 2 Newton force around the point here? Yeah, does everybody see that it's 0? You know, the reason we reviewed the torque definition here, if this, I call this the lever-on vector, R, if the force is acting right on the rotation axis, what is the lever-on vector? It's 0, right? So that's why if you have 0 here, it's just zeros for everything for the torque, okay? So if the force is acting right at the rotation axis, the torque is 0. So this is actually a strategy to solve problems like this, where you actually choose your rotation axis so that the torque due to some force that you don't want to calculate is 0, and you don't have to calculate it, okay? I'll give you more details on that in a moment. Okay, so we're going to take this as the rotation axis. Now, this will give me a clockwise torque, and this will give me a counterclockwise torque, and they'll cancel out. Okay, so the net torque is 0. Does everybody see that? Yeah. Okay. Now, if you don't believe me about that, if you know it's 0 about one point, that it's 0 about another point, we can just check. Let's try to calculate around this point. Let's suppose we take this as the rotation axis. Let's just check that it works. Then the force, this 1 Newton force, what torque does it produce at this rotation axis? 0, because the lever arm is 0, the distance is 0. But now let's see the torque of this 1 Newton guy. So let's say this length is L, and then this length will be half of L. Okay. So then I have 1 Newton. It's going clockwise with the lever arm of L. Okay. So I have 1 Newton times L, that will be my torque, 1 Newton times L. And the torque due to the 2 Newton force will be going counterclockwise. Does everybody see that? And it will be 2 Newtons times L over 2. So then the torque will be 2 Newtons times L over 2. I get the same as before, 1 Newtons times L. Right? Everybody get that? That I have a clockwise torque and I have a counterclockwise torque that cancel out. Any questions? Okay. All right, now let's go on. Okay, so the strategy here is, let me write this out because I said this sort of not very precisely. So if you find that F net equals to 0 and the net torque about is equal to 0 about some rotation axis, it is going to be 0 about any rotation axis. Okay? Yeah, so if I know it's in equilibrium, then if I calculate the net torque about any rotation axis, it would be also 0. Okay. If it was a more complicated problem where the net force is not 0, then this statement would be more complicated. Okay. Now, let me show you how a typical problem is solved, and then I'll give you the general cookbook for how to solve this problem. Okay. Let's do an example. All right, maybe I'll draw the diagram first. Maybe the diagram makes it not necessary to write everything in words. So let's say we have a rectangular block on the table. Okay, and this length here is 0.8 meters. And this is 0.5 meters. And then this is some obstacle here. It's like I don't know, something sticking out of the table, and it's preventing this corner from sliding or moving. And we have a force here exerted horizontally, F. And the words that go with this problem, force, okay, so a horizontal force F is applied to a rectangular block that hits an obstacle as shown. Force of F equals 64 newtons is just enough to start the block tipping. Okay, so now the question is, what is the mass of the block? All right, so this sound, yeah, question.
Are we assuming that the height of the obstacle is negligible?
Yes, yes. So I draw it as a dot. It's just it's like a little something stuck there. Okay, think of it as like a little hint. The size of the obstacle is nature. All right. So Does it seem like you don't have enough information to solve this problem? A little bit, right? Okay. Let me try to convince you that you do have enough information. Now, what's very complicated about this problem is this obstacle here. So first of all, let's try to figure out what exactly is being stated here. So you have this rectangle, and you pull on it with this force of 64 newtons, and it's starting to tip. So it's rotating about this obstacle. Okay, it's like a hinge here, and so there's no normal force due to this horizontal surface anymore because it's starting to tip. Okay, so the only forces acting on this block will be the force of gravity. Okay, the force of this horizontal force, and the force of this obstacle touching the block. Okay, everybody's with me on that? Okay, now, is it clear where we want to put the rotation axis? In this problem, it's kind of clear. It's a place where it's actually rotating. Okay, so if the object really has a clear hinge, some place where it rotates, you should take that as your rotation axis. So that's what we're going to do. That will be the rotation axis. So in some cases, some problems, the rotation axis is just staring you in the face. Okay. So what we're going to do is we're going to just calculate the torque due to the weight of the block. We're going to calculate the torque due to the horizontal force, and then we'll determine what the mass of the block is. Okay. Do you now see that we can actually get the answer? Okay. We set the net torque equal to 0. Okay, so let's get the force due to the weight of the block. Now, I'm going to now do something that's absolutely key, and this is worth saying several times. When you have an object like this, don't worry about this mass here, but this meter stick. Let's say you're told that this meter stick weighs 10 grams, okay? And you know it's a uniform meter stick. What you do is you pretend that this meter stick has all of its weight in the center, all of its mass at the center. This is why we did this center of mass stuff, so we can figure out where the center of mass is. But if it's a uniform stick, it's just at the middle. And then you take that 10 grams that you're told, and 10 grams is probably a little too small, probably more than 50 grams. Okay, let's get a little bit earlier. Let's say 50 grams. Okay. And it will be all that mass you can imagine as being at the center of mass of this object. Okay. So then you can take your 50 grams times g for the weight, and put that force vector, and it acts right here. Does everybody get that? You find the center of mass, put the weight there, draw the vector, and it acts there. It's not distributed over here. It's just put it at the center of mass. That's where the weight vector is. Okay, that's what we're going to do here. We're going to take the center of mass. This is the center of mass of the block. Okay, and this is our rotation point, or rotation axis. Okay, and we're going to have the mg is going to go straight down from that point. Does everybody get that? You find the center of mass of if you have an extended object, the weight vector is attached to the center of mass of the extended object. If it's a point particle, then obviously you just attach it to the point particle wherever it is, but put it at the center of mass. Okay, now here's an example of where calculating the torque. So we're going to now calculate the torque due to the weight. So let's the torque due to the weight. Okay. Let's calculate what is the torque due to the weight of the object. And here's an example of where using R perpendicular is really kind of fast. Because if we had to find out the angles, we would have to draw all these triangles, right? It's going to be a pain. Hopefully you know how to do that, right? So here's a force here. We could draw the vector R that goes from this point to that point. We could figure out the angles. We could use the sines and cosines and figure it out. However, let me show you, you can get this really, really fast. You draw the line. Remember, this is the force. This is F. You draw the line that goes straight through the force. And remember, the distance between the rotation axis and this line, that's r perpendicular. Okay? And so now the torque will be r perpendicular times the force. Okay? Everybody with me so far? Any questions? Some people seem like they're puzzled. Okay. You have the force. You want to know the torque that this force exerts around this rotation axis. So you draw a straight line through the force. You just draw a line through it. It's like coloring, right? You just draw a line, okay? It's not like coloring. It's like drawing, sorry, okay? You just draw a line through it. And now you say, what is the shortest distance between this rotation axis and this line? That's your r perpendicular. And it's just the r perpendicular times the magnitude of the force. And so now what is that r perpendicular? If you look at this drawing, what is r perpendicular from this drawing? Yeah, it's that easy. It's half this distance, okay? So r perpendicular is 0.4 meters, okay? And F is equal to m times g. All right? Okay. Any questions about that? Now let's figure out the torque due to the force, the horizontal force. So again, this is the rotation axis. Okay. And now we have this force here, F. So let's calculate the torque due to F. And once again, well, this case is pretty easy, no matter how you do it. But you can just draw a line through the force. And then you get the r perpendicular here. So what would the r perpendicular in this case be? Okay, notice it's the full length of it. So what would it be in this case? 0.5, okay. All right, so we get r perpendicular times F, okay. And so this will be 0.5 times F, that's 64 newtons. And 0.5 times 64 newtons, that's 32 newtons meters. All right, so the torque due to the weight, is that going clockwise or counterclockwise? Clockwise, kind of. Yeah, this is counterclockwise, right? That's counter. Okay. The one thing that's really annoying is counterclockwise. There's too many words, too many letters, so counterclockwise. And how about the torque due to this force here? Is it clockwise or counterclockwise? Okay, it's going around like this. So that's clockwise. So to say that the net torque is equal to 0, we take the clockwise, the counterclockwise torques is equal to the sum of the clockwise torques. Okay? So we have m times g times 0.4 is equal to 32. Let's take the units off. And so we have m is equal to 32 divided by g.4, and that comes out to 8.16 kilograms. All right. Any questions about that? All right, to review the steps, the key steps that this example is illustrating is, first of all, if it's rotating about a given point, then you take that as the rotation axis. If you have an extended object, then you find its center of mass. If it's a uniform object, it's smack dab in the middle. And then you put the weight vector, attach it to its middle. Okay? Just remember, find the belly button of the object, and that's where the weight goes down. Okay. So, like that. And you then, to get the torque due to the weight, you draw a straight line through it to get the r perpendicular vector. This works for vectors that are forces that are vertical or horizontal. And then we get the torque due to this force F here. Draw a horizontal force, that's the r perpendicular for that guy. And so we get the torque that's counterclockwise for the weight, and it's clockwise for the horizontal force F here. Okay, and then say the counterclockwise torques is equal to the sum of the clockwise torques, sum of counterclockwise equals the sum of clockwise to make the net torque equal to 0. And so we have 0.4 times mg is equal to 32, and we get the mass of 8.16. Yeah, question? So in this problem, for the torques, we're just saying the torque is 0, net torque is 0, and you don't need that. If we were calculating the angular acceleration, that's when we have tau net is equal to, well, it's just right in terms of magnitudes, is moment inertia times the acceleration. Angular acceleration. Okay. If you want to know how fast something is accelerating, rotate. Okay, yeah, question. So the thing is, we're not, right, the 64 newtons is not making it accelerate, it's just barely tipping it slowly. And that allows us, knowing that allows us to figure out what the mass of the object is. In other words, that's the minimum force required to make it tip. It's what it's saying is that the acceleration is 0. The angular acceleration is 0. And that's what. Okay. Okay, so let's go on. Let me now give you the general strategy. Okay. Here's the general strategy. Okay, 1. For any extended object, draw the force of gravity, Fg is equal to m times g, as pointing straight down from the center of mass. Okay. Number 2, find the place where the rotation axis removes an unknown force. Okay. What I mean is, if you calculate a torque about, let's say, suppose you didn't know the mass of this object, so you didn't know what is the force, the weight of this object here. If you calculated a torque about this point, the force of this object would make no computation. Okay. And so that's a trick for removing one of the forces from the problem. So find a place where the rotation axis removes an unknown force. Okay. In other words, the torque due to any forces at this point will be 0. This allows you to solve for the other forces. And then the third step is to say you set the sum of the counterclockwise torques equals the sum of the clockwise torques. In other words, you set that the net torque is equal to 0. And then if it's necessary, you also set F net equals to 0 and solve. Okay. Any questions about this? There was an example in notes that we're going to have to save for next time, but that's what we'll pick up next time. Okay. See you guys.
I do all of the extra.
Okay. So you have time to sit with me today, or when I need to see if it's what you're missing?
Okay, yeah, I do.
Okay. When we take a look at it.
Okay. When? Wait
I've
until.
well, some students might ask me questions about, but I'm just gonna answer a question. I'm gonna walk over to the help room and sit there until 4:30.
Okay, where is that?
That's at the corner of this building.
Okay, thank you.
Okay. Yeah. Okay.
On the elevator problem, why does the change of y when you calculate change of y, why does it need to calculate the position of the elevator?
Wait. You're talking about you mean the potential energy change?
Energy change of y.
Yeah. So I believe this was just what is the change of potential energy going from the first floor to some upper floor, right? So you have the potential energy here. Is this mgy initial, and then you have mgy final.
Yep.
They just want to know the difference between the two.
I do know that,
Yeah.
but it said in the question, it said the difference between the two levels was 4 meters or something like that.
Yeah.
I was just wondering why you had to account for the position of the elevator as well, because it was like the solution said it was like 33rd floor minus the first floor times the meter.
Oh no. So the thing is, they were giving you the distance between consecutive floors. In other words, the height of one floor, and you needed to know 32 floors, how high that difference would be.
Oh, yeah.
Okay. Yeah. Hey,
Hi,
so,
not class related, but is there a lost and found for this building?
yeah. If you go to the physics department office,
Okay.
you just go halfway to the help room, and you just take a left.
A left?
Yeah.
Is it South Road?
Just if you wait for me, I'm walking down there.
Alright.
Yeah.
Do you know any? You guys want